if you've ever seen sound mirrors and stuff like this. It's something from a central point that just reflects sound. You ever see these parabolic microphones on the sidelines of NFL games? It's the same thing. Transmission and reception of any antenna is the same, and same thing with any sound mirrors, okay? Now, next thing I should do is ask, are there any questions about what we've covered? And in summary, we've covered how to get, first, the magnetic vector potential if we know the current. Then we figured out how to get B and H from the magnetic vector potential doing curls. You don't need to write this down, this is just a summary. Then we figured out if we have H, we can take the curl of H and divide by J omega epsilon and get E. These are just things I'm stating that we went over. I didn't spend a lot of time on that. The three major antennas, well, four actually, we looked at are short dipole, half-wave dipole, and monopoles. Then we looked at a small loop antenna, right? And we looked at the arbitrary length antenna as well. That's really, half-wave dipoles is primarily what you need to know. That's about as long as they normally get, and they're always cut down to be not a half-wave length, but really 0.485 lambda, or until there's no imaginary point to be in 20 feet. Okay, now, that said, after the three antenna classes, then we talked about arrays. And the array is used to increase the gain by the number of elements and squared the peak gain. And it narrows, because it narrows the beam width. And frankly, it puts n squared more power on target for a given antenna. So that's the benefit of array. However, array's downside, and this is the frankness, I'm going to speak very frankly, steering a beam requires a lot of electronics. You have to have all sorts of things that either progressively shift the phase or do a time delay kind of thing. And neither one of those things are cheap or easy. I'm going to tell you that. Phased arrays are used all the time. One other thing, we always assume the magnitude of the current was the same, just the phase changes, right? That's not easy to do, and here's why. The impedance of an array of elements at the end of the array is different than the impedance of the antenna, even though they're identical antennas, of the impedance of the array at the center of the array, or near the middle. The reason is because all the elements interact with each other, and you get, really it's the impedance of all the elements acting at the end will change that from the impedance at the center one. So if you try to drive them all with a voltage, constant voltage, just change the phase a little, it won't work. Then you won't get the same current. Now there are things, I'm just going to mention this because some of you will go to work for places that mention this as if you know, because you're an electrical and computer engineer. If you want the same current at all these, there's a term called power coupling. Each antenna will have something that will couple exactly the same amount of power to each antenna. It'll vary the voltage to get the right current. You follow me on that, class? Again, more expensive. So array antennas, expensive, but they have a lot of benefits. So generally speaking, if you look at dish antennas, if you look at anything that's economical for the resident, for the user, for somebody who's a fisherman, they want as simple as possible. So they'll have a parabolic dish antenna if it's a radar and just revolve. Literally, they're not going to, that's how they're going to steer the beam. They're not going to have a phased array. Phased array antennas are expensive. That's what you see on like Aegis class cruisers or airport radars. And they can be extremely expensive, by the way. So that's a summary of the radar thing. You also learned about Friis, right? In a nutshell, what does Friis' equation tell you? Anybody?
Power received.
Yeah, if you have one transmitter, one receiver, you figure the amount of power received, right? And again, with the power received, there's two important things you need to do. When you get total power received, you take lambda squared over 4 pi times the gain of the antenna in the direction that the signal's coming from, and then you multiply it by the power density at the antenna, right? And that will give you the amount of power received, but that's not how much power you can get out. At best, you can only get half that. Then what you have to do is calculate the open circuit voltage equivalent by taking the square root of 4 times the radiation resistance, right? Times the actual incident power density, correct? Or the received power, right? And once you have that VOC, then you put that in there and you put the radiation impedance or resistance of the antenna in series with it, and then you put your load resistor to calculate the action. Do you all hear me now? This is important. That's how many understand this? Okay, now Jake, did you have a question?
Yeah, it was on the AF formula from the array antennas.
Okay, I can summarize this. Were you here for that lecture or not? You missed.
I watched it, but
All right, in a nutshell, it's this. Anytime you have sine of n psi over 2 over sine of psi over 2, that's the weight on the E field. If it's sine of n psi over 2 over sine of psi over 2 squared, that's the multiplier on the power.
you had, in the first time you introduced that, you had n plus 1.
Yeah, don't worry about that. That's because I didn't use Wentworth's labeling. Wentworth's labeling starts at 1, 2, 3, 4, da da da, n. All right? That's how you're supposed to do it. Or n might, yeah, n, right? That's the way it should be done. Yeah. Go ahead.
For the first equation, you just said what the power received is equal to like lambda over all of that, and then multiplied by the average density. Would there be a difference between that and using the power radiated, which we had to use last night for the homework?
Power radiated is useful because then you have the power density at the point, right? Power radiated is how much power you're throwing up in the atmosphere.
Okay.
The power density at the antenna that you're talking about is watts per meter squared, right? All right, let's do.
Oh, okay. So the power radiated, that would be the same as the power density if you're looking at the second antenna?
No. I think terminology may be confusing. Let me just try to make sure you're absolutely clear on this. I'm going to do a short problem. If you understand it, just hang with me. So in general, if you have a transmitting antenna, right, whatever kind of antenna, and it's got a total power it's radiating, P rad, we know that. I'm just going to tell you we know that. I could give you a current, we could figure that out, but I'm going to start with P rad. That's the total power radiated, that's in watts, right? Now I come out a distance R. This antenna has a certain gain, right? And I'm going to call it gain at theta. It doesn't matter what theta is. So now, first thing I want is the actual power density here. Well, the power density, P rad, that's the total power radiated at 4 pi r squared. This is what I try to tell people to do these things. That's the isotropic density, right? Everybody? Then we take that and what focuses it? The gain. Now we multiply it by the gain or the directivity, the gain of theta. Are you with me? The units of that are what? Watts per meter squared, correct, class?
Yes.
You're way in the back there. I'm always looking to see if you can see. Now, if I put a second antenna up here, all right, call this gain 1, and this has gain 2 at angle theta, right here. I'll call it theta 2. How's that? Label that theta 1. And I'm going kind of quick here because I got things to do. So now if I have that, I'm going to find out how much power is actually received by that antenna. Right? Power received is watts, isn't it? So I've got the power density, watts per meter squared. So I know that's going to affect it. So that's the average power density from up here. Call it this one. That's what it is. Now I take that and I have to multiply it by how big the antenna is. Because that's watts per meter squared. We need to multiply by meter squared, right? And that is called the aperture. Some people will say the electrical area. Either one is acceptable. And the aperture in terms of gain would be lambda squared over 4 pi times the gain, right? Now that's the total power received, isn't it? But that's not the power that goes to a load. What do we need to do? Well, if we had a load on this thing, and this is a cruddy drawing, our load, and we wanted to find the voltage, V load, and the current there. What we need to do is to get an equivalent circuit. That's what part of the thing is. So then we get the open circuit voltage. I'm not going to go through the proof here. Here's going to be, I'm just going to call it R radiation. Technically, it would be Z. It could have an imaginary term generally. Now, this is what the antenna looks like with an electrical model. Here, the VOC is equal to the square root of 4 times the actual radiation resistance. And this is the matched, it's assuming matched, I better call it RRAD here. And then it's times P received. Now that's not P ab, that's P received, is it? Now once we have the open circuit voltage here, then for any load, right? For any given RL, you could figure out either the current, right, by taking VOC divided by the series resistance. It would be a peak current. Do you agree, class? Or you could figure out what? The power. You could take the current, the square divided by, or times R and divide by 2, correct? Everybody? You could take V squared over R times 1/2, but that's how you would get it. You with me, class? How many see this? That's it in a nutshell. Now, I hope I answered your question, because terminology may be confusing. There's power density, that's PAB. Then there's total power radiated. Okay? Anything else? Okay, and we're good? Everybody? Okay. Did you have a question?
No, I'm good.
I don't mean to bore you. I'm trying to get through this stuff. All right, now, so we've gone through that. We've gone through the freeze transfer. That's basically freeze what I just did. We've gone through radar, power launched, hits something. The size of it determines how much power is reflected. That power reflected falls off as 1 over 4 pi r squared again. That's the power density back at the radar. If we want the power received by the radar, now we multiply it by the area of the radar, right? Which would be lambda squared over 4 pi times the actual gain of that antenna. And that's a simple way of doing it, but it's effective. And you'll find out that little bit of information will get you a long way when it comes to coming up to speed with radar. If you ever get a job, don't take the radar course. There's more to it. Most of radar, I'd say 85 to 95% of all the major focus on radar is signal processing. Let me just say this again. I said this one other time. You're in a room here. None of you are transmitting anything in terms of something that can be observed by your senses. But you look around and you can tell that's red. You can tell how far away that alarm is. You can tell that's a clock and how far away it is. That's remote sensing. It's passive radar. What your mind, through a neural network that's amazing, is doing is knowing what the light is doing. The light is the source of the illumination. Now, here's where I'll just give you a bit to see in your mind's eye where things are going. You know all about AI, stuff like this. AI is really a machine learning. Your brain is that kind of neural net. Right? Your brain does all this seamlessly. You don't even think about it, you don't. Well, if you have a neural net that's smart enough, it can figure out electromagnetically over a certain frequency domain what's out there. And then it can figure out, just like you do with photons of light, what waveforms hitting a certain structure and reflecting back to it. Just like bats use sonar, but they create the sonar. You can use this. It would be a neural net to do this. But you can use the same thought. Instead of photons of energy, that's very high frequency, basically electromagnetics, it would be microwave. And then you could have a radar that never had an active emitter. You all follow me what I'm saying? Now that is incredible, because then, first of all, you couldn't jam it. It would be a wide band. Second thing is, they wouldn't know where you are. Biggest problem with planes, stealth planes, if they want to interrogate a region, they have to give themselves up or have a second plane interrogating the region with radar and illuminating it. So what I'm just telling you is something else that all these remote delivery systems that Google, Amazon, the US Post Office, and military are working on with their drone deliveries, what they have to have is extremely good sensors. And if they could ever get a passive radar to work effectively in a city environment where there's sun, then they would have a gold mine. Follow me? Give you something to think about. You can look it up. He actually sent me something about radar. I appreciate it. If you want to send it to the class, you can. It has nothing to do with what I just said. That's called passive radar. And you can even look up noise radar if you're interested. So, now, that said, the next thing we're going to do. Any questions before I get into this lecture? I see I'm moving too fast, it's 'cause 3 or 4 things I want to mention, but I know we got to quit, and I know your minds are sort of geared towards that. So after chapter 8, the next thing we're going to do is chapter 9, and that's EMC. Let me just try to do this, and this is the course I teach. It's an electromagnetic compatibility and interference. Really, that's a misnomer in a lot of ways. What we're trying to do is figure out when you implement a system where the problem is. Most of the time in the real world, when you get electronic systems that are rather sensitive, like radar, telecommunications stuff, there's all sorts of problems that are unseen that are called incompatibility or interference. Either one's useful. So what we do in the United States to try to minimize that amount, especially at hospitals, around airports, is we have rules called FCC guidelines, and they limit the amount of power transmitted in airwaves, as well as the amount of power that can be placed into the walls over certain frequency domains. All right, because it's called conducted emissions, but when that wall outlet that you always is that's 60 hertz. It's basically at what 117 volts RMS, right? What you don't know is that is a perfect transmission line. And that transmission line, you can put 200, 300 kilohertz signals on accidentally as it feeds back. Right, you got a transformer to buffer the high voltage, but you can put easily milliwatts, tens of milliwatts on there that are going to be microvolts, millivolts, maybe even close to volts. Admittedly, it's a different frequency, but that thing can interfere with everything, all pieces of equipment. Does anybody ever remember if you put an AM radio on or anything that had amplitude modulation, turn on a hairdryer, what happened? Y'all remember that? Anybody notice a hairdryer causing AM radio to beep? Has anybody been in a car that had the old plugs and you're driving down and you have AM radio and you hear when you accelerate, you hear in your speakers, right? Well, that's mainly, can't say for sure, is conducted emissions. All right, through the walls, the hairdryer for sure. That through the electronics of the car. That's the stuff that I teach how to mitigate. And by the way, without giving away how I know this, some of the most highest paid engineers out there, if you go to AdTran or really Dynetics and stuff like that, are going to be what's called compliance engineers. They're the guys that know everything, that fix things when they don't work in the field. Because you can buy cell phones, especially, are bad about this. I had a guy give me a story about how much money they cost to fix these cell phone towers if there's like lightning problems. There's certain towers that get struck all the time. That's an incredible amount of money, mainly because of the hourly rate of the engineer trying to figure out how to do it. So I'm trying to give you a little heads up. Both radar and EMC/EMI, and that's just not what it's about. It's about a lot more than that. These are things that can be gold mines if money is what you're after. It's also very challenging too. You're a detective, and you're the worst kind of detective. First, you don't know what's wrong. You don't know how to fix it. So you coming in there, and you just know how things should work. You don't know why they're not working, so you have to eliminate possibilities. That's it in a nutshell. That's what we're doing here. So now with electromagnetic interference, Dr. Wentworth's book in the early pages, sources. Pick one. Lightning, right? Lightning hits, there's problems. And think electrical always. Think communications. Think your TV. What hurts TVs? Well, lightning strikes your area, it'll blow up if it's in old days. If it hits the cable, anybody ever lose a TV because of lightning? I know, so my wife did. Long ago. Yeah, lightning's not fun. It's not fun on the water either. If you're ever on a boat with a long antenna, it's kind of scary. Second thing that causes this stuff is unintentional interference. That laptop radiates a signal. If for whatever reason, if William here decided to hot rod his thing and do some engineering back there and not properly shield it, his laptop could interfere on a lot of things like your cell phone. Follow me? So there's all sorts of things like that that are sources. Unintentional, right? You did some work at that. And intentional, by the way. Because that's when we get into, well, what do you mean intentional? Well, the military stuff. I intentionally want to prevent somebody from getting information. They do it with cell phones. If anybody ever, this is in some movies, you sort of interact when they're blowing up roadside bombs with their cell phones. They had a noise blanket that eliminated the ability to communicate with a cell phone. There's stuff like that. So the military is interested in doing that. And that should make sense. But sources themselves are everything. He gives all this. So the first thing we talk about, well, how do you model these sources? First, we have to start with the most basic thing, and that's a wire. We've got to figure out electromagnetically what things look like. Then how those things are going to, I'll use the term catch electromagnetic energy that's not wanted. And then what do we do about it? I mean, once we know where the problem is, what do we do about it? So, let me do it this way. We're going to start with a wire. We'll go for wire, the inductance and resistance of the wire, both AC and DC. Then what I'm going to do is resistors, capacitors, and inductors. I'm going to show you the equivalent model of different frequencies. So first put down low frequency. You can put down DC too. By low frequency models, if you have a wire, write this down. It's in this book, but I like to be clear about this. If I have a wire, and this is the cross section of the wire, of length L, and the wire is going to have a conductivity of sigma. It's going to have a radius of A. All right. That radius gives me a cross-sectional area equal to pi A squared. And some of you remember this. The resistance of this wire I can figure out if I assume a certain current going down there. I could get the current density J. You don't have to write this down, but I'll just go through it. If I wanted to figure out the resistance of this wire, I would start by assuming I don't know if you remember this from EMAG 1. Then you would get J, and J is the current density. That would be I over area, right? Or over pi A squared. Y'all remember that? Remember what happens after J? We're trying to get the resistance. I assume current, I need to calculate voltage, right? What's my next step? Get E, right? If that's J, the current density, we know sigma E is the electric field, is it? Correct, class? That would be along the axis of the wire if current's going in normally. And we could say that E itself here was equal to I over pi A squared sigma, right? Now I've got the electric field. I'm almost there. That's volts per meter. And I know the electric field would be in the direction of current. We're assuming the current's flowing that way. That would be the electric field to get the total voltage between here and here. Right? I would say, technically, what would I do? I would integrate E dot dl over the length of the wire. Do y'all remember doing that? That's how I technically do it. I don't need to be that fancy. I know the E field's in one direction, it's constant, right? Integrating E dot dl, E is constant, take it out in front, integrating dl gives you L. It's just equal to what? E times L. In this case, it would be I over pi A squared divided by sigma times L. And that would be the actual voltage. I'm going through this kind of quick, but this is old school stuff. You had this before for physics and electrical. And finally, you get the resistance, the DC resistance, right? The DC resistance would be magnitude of V over I, or it's proportional to the length, inversely proportional to the cross-sectional area, and inversely proportional to sigma, right? So that's the length. It's always proportional to length resistance. Inversely proportional to the area, right? Increasing area is like putting resistors in parallel. The net resistance goes down. And it's inversely proportional to sigma. What's the conductivity of copper, any metal, roughly? 10 to the 7, 5 times 5 points, what, 5 point something times 10 to the 7?
5.8 times 10 to the 7th.
Yeah, and that will vary based on the types of copper. There's blended copper, but it's about 5 to 6 times 10 to the 7th, right? 1 over that is about 10 to the minus 8, 10 to the minus 9. That means resistance of copper is very low for general proportions of L over A, right? You know that. It's extremely small. However, the resistance of something like, you know what mica is, or ceramic, or anything like that? What the conductivity is? It's got a conductivity. Well, what is it for air? This is a good one for you guys. You're electrical engineers, you should know. What is it? What's the conductivity of dry air here in front of us? About. It does vary on moisture. Well, it's about 10 to the 12th, right? 10 to the 13th, 1 over ohm meters. Figure, I mean, if you take a look at, I'm sorry, 10 to the minus 13, 10 to the minus 12. What I'm saying is, it's literally 18 orders of magnitude lower than what it is for copper. Which means if I put a voltage source here and I have 2 wires dangling, it draws almost zero current. It just can't. This is like a resistance that's extraordinarily high, almost a vacuum. Follow me? So it gives you perspective. That's the DC resistance of this wire. How about if I put it here? All right. Now we get into something called the skin depth effect, because we know when we have a certain amount of current flowing in a wire at a variable frequency, it hugs the surface. Do y'all remember me doing this? The skin depth causes it. So let me redraw this. When we have AC stuff, this is going to be a higher frequency, and I'll qualify how high. It has to be in a second. Now I take a look at this, and I say all that current, if this is radius A, then all that current is going to be 1 skin depth D. And the skin depth is 1 over the square root of pi f mu sigma, right? That's sigma of the wire. You all remember that? How many do? All right, skin depth is something you got to get used to. You're going to use it all the time as an electrical engineer. All right, now I know all the current is really limited to 1 skin depth inside, but there's one qualifier. And put this down as star. We're assuming that sigma, the skin depth, is less than the radius A. Now, if the skin depth is greater than radius A, then you just default to that equation for resistance. And skin depth is inversely proportional to frequency. That's all it is. And very, very high frequency circuits that couple power basically are hollow pipes. I worked with one on my master's work. It was just a hollow aluminum pipe they ran a coolant through, because having a solid aluminum pipe wouldn't help. There's no current going through it. It was 13.56 megahertz. So what's the actual, if this is length, what's the radius of this? Well, what's the resistance of this? Technically, the resistance of this, I'm going to call it AC, or high frequency, would be the length, right? And this is assuming this is true. It would be the length, and it would be divided by sigma, but now the area would be pi, and it would be A squared minus the quantity A minus the skin depth squared times sigma. Take a look at that for a second. We did this. I want you to just think about it. Let me slow down a little. Let everybody catch their breath. I do want to tell you, if you want to bring food and drinks in here, you can bring any drink you want, just don't spill it. And any food you want, as long as it doesn't go crunch or make noise. Something there. I don't know, candy bar, piece of bread, something. Okay. Or, I guess, Chick-fil-A. Guys, is that thing still open or not? I used to have people eat in my classrooms all the time. Since COVID, I don't think I've seen anybody here even bring a sandwich or anything, have they? You all remember those days? We used to eat in class. We used to have fun. Those days are long gone. Anyway, the reason I'm saying that area is pi times A squared, well, that's the whole area, right? And then I have to subtract off that inner area. Well, that inner area is pi times pi over, it's really pi times A minus the skin depth squared, right? And if you want to approximate, do it this way. Now, if the skin depth is much less than A, all right, say it's a tenth of A, then you can just say RAC looks like L over pi, and then it's just going to be 2 pi A times sigma. Here's what happens. Oh, 2 pi A sigma times the skin depth. Do it this way. I'll explain this. Here's what this is. If I cut this thing right here, I want to make sure if I catch it. Take that, just cut it in one place, and unroll it. Right? What's the total length? The total length of that thing would be 2 pi A, right? It would be the circumference. What's the thickness? Skin depth, right? Skin depth times 2 pi A is the area. That's where that comes from. Okay? You can prove it from this if you want. This is the golden rule. Yeah?
Where does that second pi out front come from?
That's from a mistake. Thanks, Jay. Okay, are we good? All right, so far? Now, I'm going to tell you this. So far, and this is the last thing before the quiz. That's resistance. AC, DC for wires. How many understand that? Next thing is inductance. Well, I don't know if you remember what inductance was for a wire. Let me put it down here. L. Well, LDC, you remember what it is for a wire? There's one really cool thing about this. What is it per meter? Isn't it mu0 over 8 pi? How many remember that for inductance of a wire? Remember that or no? Look it up. It's times the length. So it's mu0. Well, really mu relative times mu0. I better be careful. Because it's an aluminum wire. This is DC. Over 8 pi right here. Let me actually see if I can get that. All right, this is on page 504. Right below equation 9.5, it says Li equals mu over 8 pi, and then it has times L, because L is the length. And what's neat about this that I take from it, remember this is DC. I'm just going to put mu here. Right here, times the length L. Then it doesn't matter on radius. You can have a thick wire or a thin wire. The inductance per meter is that. Now that is internal. And I want to make sure, so you write down internal inductance. What that means is this is associated with the magnetic energy inside the wire. Make sense to everybody? That's just magnetic energy inside the wire. But we know when you have a wire, most of the energy, just think of the field lines, is that we have H fields all over the place, right? H fields cause an energy density of 1/2 mu H squared, right? Magnitude. Energy density integrated over the region where the H field exists would give you the total energy, which is many orders of magnitude at times greater than that. But the real problem with estimating inductance correctly, there's internal that we have. But the thing about it is, how is the return current getting back to the source? Because that return current creates another H field that cancels a lot of the original H field. So they can't give you an inductance per meter for the external wire. It depends on things that are in the environment, and there's a whole different school of thought on how to do it. It's called partial inductance that Dr. Wentworth just mentioned, and I don't want to get into it. Now for AC, I think he's got this in there. Yeah, here's what happens. This is DC if we have AC inductance. Here again, skin depth is less than A. Then we can say LAC, or high frequency, will be equal to LBC here, and then it's 2 times skin depth over the radius A. Now he has that in his book on page 9, or it's equation 9.6 on 505, but he doesn't put it in terms of LBC I put it in terms of this, LBC, because that's easy to remember. Are you with me? All right. Could you do me a favor too?
Is that 2D over here?
Say,
Is it 2D?
It's 2 skin depth.
skin depth, I'm sorry, skin depth. Could you do me a favor and help me separate people? Could you fill up this pseudo row? Leave this pseudo row. This is an interesting one. Empty. Fill up the
Yeah.
one behind William here.
Wait, sorry.
Leave the one with